Yeah, so the topic today will be about probability calibration for predictive machine learning. It basically covers some recent work for the past few years, particularly regarding recent problems with deep learning, and a few works that I've done within my group. So I'm, as Andy said, I'm a postdoc in the University of Bristol, and I'm in Peter Flack's group. So before I start, following the previous introduction, so I think especially on the topic of uncertainty and confidence. So in my view, so there is actually two levels of uncertainty. So the first level, so as in the Bayesian setting, and particularly with Bayesian neural networks, is basically whether your model should be confident on the prediction itself. So I might predict a probability of 1.0, but I'm not really certain about this prediction itself. And there is the second level of uncertainty that is mainly on the predicted probability, such as when is 1.0 probability, I'm pretty certain and confident on it being a positive label, or 0.5 as in the frequentist setting, meaning that the label chance will be half and half. So the reason I'm saying this is that actually, as you will see, the topic of probability calibration mainly focus on the uncertainty over the labels. So whether the labels, the probability vector matches the distribution of the target label. And it's at least as far as I know, so far there hasn't been many work focusing on calibration on the uncertainty in terms of model parameters or model confidence. I shall elaborate a few points towards the later slides. Okay, let me actually start the timing in case that I run out of time. So yeah, so the to-talk list for today is basically to give a brief view of the field and some typical method on the evaluation and approaches to improve calibration. And in particular, I will talk for a few definitions in the binary setting, multi-class setting, as well as the regression setting. So first thing to start, let's start with a real life scenario, which I personally experienced in the late evening, and when I was reading my phone and the battery ran out, and I saw the red picture, which basically means that I need to get a new pair of the charging cable. Because it's very late and I'm already in my bedroom, I didn't really want to go downstairs and open my laptop and to order things. And then being a machine learning researcher, I'm always interested in trying new stuff, particularly for our recent development with NLP. And so following this example, I actually tried a few things, such as buy me a phone charging cable. And with technology, recent technology developments, we actually end up with many options, such as Type-C cable, micro USB cable, or Apple's Lightning cable. So if I say that buy me a phone charging cable, what I want my device to do is actually figuring out that I haven't specified a particular type of cable. So it might be good that the model under after the NLP device can actually figure out among the population of people want a phone charging cable. It might be Type-C, it might be micro USB, or whatever cable. So the probability for estimating on these labels should not be very confident or to be very high on a specific type of cable. In this case, I want the device to actually clarify with another question. So which type of the cable do you really want? And the top three choices are. But on the other hand, if I explicitly say, buy me an iPhone charging cable, And what I really want the model to do is to figure out is almost a probability of 1 that I want an apple cable. And then the device might say something okay that I want to order something that can be delivered tomorrow to my office. So yeah, it's just a very simple example. So to indicate that uncertainty is important. So not only we don't necessarily only want the thing to give a better accuracy or a better X-score or some generic evaluation metrics you see for in common machine learning researches. But it's also good that we can actually have accurate predicted probabilities as a way to evaluate the uncertainty. And of course, being confidently wrong or unconfidently right can both hurt. If it's actually being confidently wrong, it will end up buying me the wrong thing without asking me my for further ideas. Or unconfidently right, meaning that it will keep asking what do you really want, and while the answer and your intention is quite clear. And a good probability estimation is non-trivial when picking the answer. So I mean, if you think these days with all the business models, with recommendation systems, with NLP, with computer vision, so there will be a few things that you can actually derive to further increase your user experience, or in this online shopping cases, such as return costs or the number of deals it can make. So as I said before, so today we are only interested in this particular kind of confidence or uncertainty, that is the confidence or uncertainty on the predicted probability on the labels. So in this particular case, I just put a table here as a toy example, where the left column gives all the queries, as keywords, and then the model prediction on a specific type of cable given the corresponding query, and in the databases that whether the customer eventually bought the corresponding cable. And here comes out the definition of calibrated probabilities. So if we just look at this 0.75 prediction on the Type-C cable, we will say this probability is calibrated if and only if among all the customers with this among all the queries that receive this 0.75 prediction, so charging cable or phone cable, that actually there is around 75% of customers that indeed bought the Type-C cable, so that the predicted distribution on the Type-C cable matches with the target variable. So this is the definition of having a calibrated probability measure at the value of 0.75. So now let's look more formal definition. So from the simplest scenario of binary classification, suppose we have a model that maps from some feature space X into interval of 0, 1 as a probability estimate for the positive class. Because I is a deterministic function, now we can actually say that we have a further random variable denoted as s equals to fx. And we can say I is calibrated if and only if for any s value within the range of 0, 1, given I being a particular value, the probability of y being positive is indeed this value of small s. And it's a similar to example at the bottom side, where the color of the dots representing the classes and the value representing the model prediction of the positive class. That is the blue color. So for the right group, we can see this group all receiving the same probability value of 0.75, and 3 out of 4 dots are indeed blue. And for the left group, when the value is actually 0.4, 2 out of 5 are indeed blue, which also indicates that this 0.4 probability estimate is close to be calibrated. I said close because simply here we only have limited data points, but just as an illustration of the idea. So we can also take a closer look with some real examples, not real as in real data set, but at least we have a running model and some data set and samples drawn from it. What I did here was I assumed to have a synthetic data set where so if you look the left figure, the horizontal axis is our feature value, that is x. And the vertical axis is the predicted probability. Because these samples are drawn from a synthetic distribution where I know the underlying parameters of distribution, I can actually calculate the true posterior probability on the label, that is P of y given x, and is indicated by the black line. And then what I did was I simply just train MLP two-layer multi-layer perceptron, so it's not really deep, shallow neural network. And from sklearn, just with all default settings. And as you can see, it ended up with giving the predicted probability as indicated by the CERN line. In general, as you can see, because the data set is fairly simple and the model doesn't do very, so it also should I say basically doing reasonably well. At least the fitted line follows mostly close to the underlying true model. However, as we can see, there will be a few areas that is actually not overlaying to the true model. And then if we move to the right figure, which is known as the reliability diagram, what we did was that for any model, for any data point, be it blue point or red point that receive probability estimation of x, we move it to the horizontal axis. So as you can see, the right figure, the horizontal axis is indeed x, which is the predicted probability. And the vertical axis is the posterior probability that conditioning on this probability estimate, the probability of the label being positive. So as the figure indicates, with the true model, we can see it gives a resting diagonal line saying that given any probability of s, the probability of the target variable is indeed s. So that follows our previous definition of a calibrated binary model. However, with the MLP or the shallow networks, we can see although there are a few areas that is quite close to the true model, but there are also a few areas you can see it significantly overestimates the probability or underestimate the probability. And this is why we want to further calibrate the model. And that's why we say this MLP model is not technically calibrated in terms of probability estimates. So there are a few approaches that you can evaluate the level of calibration. Actually, even for this all this evaluation method, it can already be a full talk that beyond 1 hour. But given that I only have something like half an hour to 40 minutes, so let's just have a brief view. So the first thing is something known as calibration arrow. The idea so is basically to only evaluate calibration and not evaluating anything else. And the most commonly seen one is the expected calibration error. The analytical form is to basically, in a binary setting, you want to integral from your distribution of the score, so basically integral from 0 to 1, and the P of I is denoting the density of your score or probability estimate. And with each specific i's, you want to have the absolute difference between the estimate and the true posterior probability given x. So that's why the name of expected calibration error comes from. So all the bit within the absolute sign is the calibration error, and by having interval with the density of s, it gives us an expectation. However, in practice, there are few issues with calculating this ECE. First of all, normally we don't have enough data to actually estimate the P of Y given a specific probability of S. And the second of all, the density of S is also not available, so you have to do some estimation. The most common approach is simply just to have empirical binning. So you divide your S into a few bins, such as the bins within 0 to 0.1, and then you calculate the number of samples within the bin, as well as the number of positives within the bin. And then you can calculate all this ECE in an empirical approximation. And the second category is known as proper scoring rules, and which the most common one is actually the logarithm loss, which is also known as negative log likelihood, or cost entropy, as normally what you fit with deep learning, and alternative things such as Breyer score, which is the squared error between the probability vector and one hot encoded label vector. One thing to note here is that proper scoring rules are not only evaluating calibration. In fact, proper scoring rules are optimized if and only if the model achieves the best optimal probability. However, so for those of you familiar with the literature, the proper scoring rules can actually be decomposed into calibration laws and refinement laws. So calibration laws is basically just as in the above calibration arrow that focus only on calibration, and the refinement laws is basically regarding the losses that comes within the source distribution, as well as the additional loss introduced by your model. The reason to mentioning proper scoring rule here is that, especially with my recent reviewing experience, when people working on calibration, a common mistake is to focusing only on calibration error. However, if you only focusing on calibration error, you might end up with actually a poor model. For instance, if you just have a weather forecast model that predict that the probability of rain in the UK is 0.9 through the whole year, that can actually be calibrated because the marginal probability of raining in UK is probably 0.9, but it doesn't really make much sense as a classifier, so it has no or very weak discrimination power. And for those of you who are more statistical person, there has been recently some developments that to perform statistical test of calibration. Here is just one of the early paper back to AI 2019. The idea is that to assume your model, so your null hypothesis is not calibrated, and your your null hypothesis is calibrated, and then you can actually performing some statistic test on the calibration error or even proper scoring rules, and to using the received statistics to whether to accept or reject the test. So I wouldn't go too much details, but you can actually go to check their papers, and they have been doing some recent works to further increase this to multi-class or even regression scenario. Okay, so the next topic is post-hoc calibration. As we already seen, that models can be uncalibrated due to several reasons, and in particular, deep nets, while it can actually give a pretty good accuracy, but it's not very common that it can provide uncalibrated probabilities. And since, in particular for deep net and in vision problems, a single model can take days to train. Alternative solution is to, instead of asking the models to be calibrated as training time, but to consider some post-hoc approaches that can improve the level of calibration. So in a binary setting, we can simply use a function, or indeed any function, that maps from the interval 0, 1 to inter 1, that to make the uncalibrated probability to be better calibrated. In this particular tool example, as we can see, for the left group, the 0.9 is clearly uncalibrated because we know the true answer is 0.75. And similarly for the 0.3 group. And with the empirical data observation, what we can tell is that the 0.9 should be mapped to 0.75, and the 0.3 should be mapped to 0.2. And so the idea of post-hoc calibration is indeed to organize your data set into a calibration set, where you can use the probability, empirical observed probability, and the previous estimate probability to fit this calibrator function so that your final result basically more calibrated. Most typical solution for binary problem is isotonic regression, which basically fits a monotonic curve to minimize the squared error between the curve and the labels. So in the binary setting, you can see that the negative labels are 0 and the positive labels are 1. And essentially, there is some mathematical proof because it minimizes the mean squared error. You can actually show that it actually minimizes the Breyer score. But with the limited time, I wouldn't go too much details. This is just a simple example with the MLP example we just seen. If you check the leftmost figure, so that's in the feature space, and after the calibration, the dashed black line actually follows more closely to the true model, and this is actually you don't really have to train the whole model again. And in the middle is another key visualization in the domain of calibration known as the calibration map. This basically tells you, or as in the previous example, how your calibrator is mapping from a calibrated probability and a calibrated probability. And the rightmost figure is again the reliability diagram as a way to inspect the level of calibration. And we can see, although the dotted line after calibration doesn't actually follows the racing diagonal because we only have a limited number of data points. But compared with the uncalibrated MLP classifier, it already shows various improvements, and that is actually being closer to the racing diagonal. And recent work from Peter and Melis. So Melis was previously a postdoc in my team, and he's now a professor at Tartu University in Estonia. So they were basically trying to build a calibration from the beta distribution, which is commonly used to model the hyperparameter for a Bernoulli distribution. And to save time, beta calibration function is a parametric function, and the mathematical form is actually quite simple. You can think it just as a logistic regression, but the feature is the logarithm of the estimate i's and the logarithm of 1 minus i's, which is the natural representation of the beta distribution. What is important with the beta calibration is that being a parametric calibrator, it has limited calibration maps that it can provide, but it includes a few interesting calibration maps. For instance, if you check the bottom left one, that with a specific setting, it can actually give a diagonal calibration map that is not changing the probability at all. That can be actually quite useful as a prior or regularization when fitting these beta calibrations. It's saying basically, unless the data strongly suggests so, please do not adjust the probability easily. And if you check the right most figure, it can give a similar shape as typical logistic regression, that's the sigmoid curve, and as well as the inverse the sigmoid curve, as in the middle right figure, and various useful shapes as indicated by these groups of figures. So that's a recent approach for the beta calibration. Okay, so now we observe, yeah, it was for binary classification. And now we move to the setting for a multi-class calibration. So it's basically the same notation. We have a model F that maps from feature space to a target space. But instead of an interval 0, 1, now we assume the space Sy is a probability vector space. That's basically a k-dimensional vector, and is all larger or equal to 0 and sum up to 1. Again, denote S as the random variable of model predictions. So S is a random probability vector, and F is said to be multi-class calibrated, or in short, calibrated, if for any probability vector and for any target class J, the following equation holds, that given S being a specific probability vector, the probability for the target to be the J's class is indeed Sj. That is the J's dimension of the conditional probability vector. Again, with the two example, we see what with the, because we now have three classes. So we use the blue, red, and yellow coding. So with the red group, as we can see, the estimate is 0.75 for blue and 0.25 for red and 0 for yellow, and it matches the empirical observation. So that's is very close to being calibrated. And with the left group, similar thing. So we have 0.2, 0.2, and 0.6 probability distribution, and that matches the empirical frequency of the colors. However, one particular issue with the true multi-class classification, as we can see, is actually live within a higher dimension. So the condition is actually on a full probability vector, and it is slightly harder to think in terms of the calibration maps as well as the reliability diagrams, which was indeed, as we can see, can be visualized by a function from 0, 1 to 0, 1. So some early researches that's focusing on multi-class problem was basically trying to simplify it into a binary setting. And here I just give two common simplified versions. The first is known as confidence calibrated, or top predicted probability calibrated. The idea is rather simple. So you assume a random variable S hat that is the maximal predicted probability within your vector. For instance, if you have for a multi-class problem, if you have a 0.9, this S hat will be 0.9 because it is the highest probability value within the vector. And the Y hat being the argmax of the probability vector, that is basically the winning class. And the confidence, the concept of confidence calibration, being confidence calibrated is actually denote the highest predicted probability is S, given it is S, the probability that Y being this highest class is indeed S. As you can see with this selection on the top predicted class, it can effectively change the problem into a binary setting, where, as you can see, S is a number between 0 and 1, and the expression Y equals to Y hat is a Boolean expression. It can either be positive or negative or true or false. And another more easier to understand concept is simply class-wise calibrated, which is one vs rest calibrated. We can simply just conditioning on the jth dimension of the probability vector being a specific value of S, and given this condition, and Y, the probability that Y being the jth class is indeed S. So with both of these definitions, you can simply use all the approaches, disregarding its evaluation or post-hoc approaches, from binary setting to directly apply to this two versions of simplified multi-class calibration. However, for the true multi-class calibration, so in the true multi-class scenario, the problem can be slightly harder, as we know that inside we need a calibrator function that is multivariate, that is, it maps from a target probability vector space on Y, that is Sy, to Sy to fully adjust the probability simplex. For deep nets, it is also very common to not only building calibrators on the final probability output, but it is also common to take the vector layer before softmax, which is a k-dimensional real vector, and build a calibrator C that maps from this k-dimensional real vector space to the corresponding target probability vector space as a replacement to the previous softmax operation. And one of the most simplest case is the temperature scaling, which basically has a single parameter T, and its input is, as I said, is the pre-softmax layer that is k-dimensional real vector denoted by Z. And you can think it's just a softmax, but before the softmax, you have the temperature multiplied to your pre-softmax layer. And this was actually one of the baseline approach that from the on calibration of modern neural networks back to SML 2017. Here is just again a quick view with the tool example. So the top figures is similar to what we have seen before, but it's a class-wise visualization with class 1, class 2, and class 3. So again, as you can see, beyond the blue and the red points, I add a third class that is around the middle and indicated by the yellowish, the green dots at the bottom of the figure. So the bottom row is the calibration map, because as we have seen, we can no longer visualize it as a 1D function. So I use probability simplex. The easiest way to understand this is tells you how is the calibrator change the uncalibrated probability. If the color is more reddish, meaning that the calibrator is increasing the probability prediction for a specific class. And if it's around white, meaning the calibrator is not adjusting the probability, uncalibrated probability. And if it's bluish, meaning it's reducing the corresponding probability values. And as we can see, if it's this particular example, because with temperature scaling only has a fixed parameter of t, it gives the same adjustment to all the three classes, disregarding, as it's shown by the top row, that they are all uncalibrated with different manners. And as a result, particularly with the top right figure of class 3, we can see the after calibration is basically the same as before calibration. So temperature scaling doesn't do much here. Okay, so I shall be slightly faster since the time left is limited. So more recent work by me and our group is known as the Dirichlet calibration, which, as you know, that Dirichlet distribution is a generalization from beta distribution. And again, it's basically a linear model, but on the logarithm of the probability vector, that is the natural representation of Dirichlet distribution. And the good thing with it is that given that it's a fully linear model in the logarithm space, it can actually give better adjustment to every class separately. And in particular, if you check the rightmost column, now the Dirichlet calibration is capable of fixing the issue on class 3, and the dotted black line is more closer to the ground truth, that is the gray line in the background, and change and make a lot of change to the uncalibrated model. Okay, so just things, yeah. So we move to the question of regression model. So actually, calibrated quantile regression is a topic that has been talked a lot. Actually, there is some history in the statistical field, and using the similar notation, if we assume a quantile regression model is denoted by G that maps from X and value between 0 1 as the quantile and into a real value that is the domain of Y, and denoting Y tau as G of X tau, that is the random variable for the tau's quantile prediction. And we can say G is quantile calibrated if and only if given any tau within 0, 1, the following holds. That is, the target of Y being smaller or equal to Y tau, the probability is indeed tau. And similar for the two example, you can see at the bottom, the 0.1 quantile is the bottom blue dashed line, actually covers about 1 point below it and 9 point above it. So that says that this particular quantile is calibrated. And the post-hoc quantile calibration, so it's only recent that people start to realize we can actually use this to use this post-hoc approaches to improve quantile calibration as well. And this was from a 2018 SML paper from Kuleshov et al. What they did was they realized the Monte Carlo dropout uncertainty in a regression setting from a deep net is actually uncalibrated. And then they propose to use actually a binary calibrator because quantile is within the space of 0, 1. And they can actually use a binary calibrator, such as Isotonic Regression, as a post-hoc calibration tool to improve, the estimated quantiles. And again, you can actually organize a calibration set and calculate the imperial frequency and build your calibration map. However, so a more recent work from us is that we realize quantile, the concept of being quantile calibrated doesn't closely follows the case as in classification. That is, the quantile is a global setting instead of a local setting for every individual prediction. And we propose a concept known as distribution calibration. So yeah, the time is limited, but it was published 2 years ago in SML, known as Distribution Calibration for Regression. The idea is that instead of conditioning on the quantiles, we assume the target space Y is a space of probability density functions instead of a probability vector, and we assume conditioning on any specific predicted density, the distribution of Y indeed follows the probability density functions. Here is just a simple comparison between distribution calibrated and the quantile calibrated. As you can see, the quantiles are defined across the feature space and is globally defined, while distribution calibrated asks your model to be actually locally calibrated with each group of predictions. So to basically, while we can also do post-hoc distribution calibration as well. Well, in the quantile case, we can just use a single binary calibrator. It can be seen that with a distribution calibration sense, you actually want to build separate calibrators within each local group of predictions. I don't really have time to cover, so this is some approach that we build up basically as a combination of Gaussian processes and the beta model. Yeah, sorry, because it's a Bayesian setting thing, I was quite it would be very interested if I have actual time to talk about this, given that I think this group actually has some quite good Bayesian background. But anyway, just before I go, so a good example would be, so this is just a toy example where the top figure, the heat map is probability densities, and the bottom is the quantiles. And as we can see, particularly if you look at the right column, with the isotonic regression for quantile calibration, it actually doesn't fix the density a lot. So there is still some densities within the two groups of yellow dots where there is no observations as well. But with the distribution calibration, things can be effectively fixed. Okay, so takeaway messages. So the level of calibration is the goodness about the probabilistic predictions. So it's on the prediction level, and as I said, it's nothing about whether the model should be confident or not. So it's not about model, but about the target variables. And the post-hoc calibrators are often handy when you have pre-trained models at hand, such as DeepNet. And for regression tasks, distribution calibration can actually provide a better overall uncertainty quantification because it's more local. Okay, thanks. And this is some takeaway references. I think I will later send the slides away for reference.